Hi Year 13 and welcome to this video on acids. In this video we're going to learn about strong and weak acids, the differences between them, and how to calculate the pH of both. We're also going to look at a new concept called Ka. So first of all, acids. What are they? Well, hopefully you can remember from previous years that acids are proton donors. That means they give away H+ whenever they react. So if we take an acid like HCl, hydrogen chloride, and place it into water, what would happen is the acid will lose its H+ to the water completely, forming Cl- and H3O+. Because the water has received an H+, it's acted like a base. Because the HCl has given away an H+, it's acted like an acid. And we can see that once the H+ is removed from our HCl, it's going to leave us with Cl, and because we've lost a positive as well, it's going to leave us with Cl-, explaining that product. Because our H2O has gained an H+, it's going to be H3O with a positive charge, the hydronium ion. So all acids will donate protons. It's also good to remember that when an acid reacts, it's going to turn into its conjugate base. So Cl- is the conjugate base of HCl. H3O+ is the conjugate acid of H2O. So it's good to keep those terms in mind as well. Acidic solutions will always have a higher H3O+ concentration than OH- because of this process, that donation of H+ to the water, which means their pH will always be lower than 7. Let's have a look at strong acids. So strong acids completely dissociate in water. So if I take any strong acid and put it in water, it's going to completely break apart into ions. For example, again our HCl. So if I took 0.1 mole of HCl, it would react with 0.1 mole of water to form 0.1 mole of Cl- and 0.1 mole of H3O+. There is a complete dissociation. Every single one of those that I put in has completely broken apart to form entirely these. So this is actually our hydrochloric acid solution. There's none of this in there. We can easily calculate the pH of a strong acid solution. If we take our pH equation, pH equals the negative log of the H3O+, well, we know the H3O+ concentration because all of our acid has completely dissociated to form hydronium. That's a 1-to-1 ratio. So whatever my concentration of acid is, it's the same as my H3O+, assuming it's a 1-to-1 ratio. So my H3O+ concentration for this solution will be 0.1. Plug my number in, and out comes the answer of 1. So a 0.1 mole per litre HCl solution, which is actually this, is going to have a pH of 1. Now, how do we know if we have a strong acid? How do we know it's not a weak acid? Well, the key thing to remember is there are only 4 strong acids: HCl, HBr, HNO3, and H2SO4. Hydrochloric, hydrobromic, nitric, and sulfuric. Now, when it comes to weak acids are different from strong acids in that they only partially dissociate. That means they form an equilibrium. So we're not having that same extent of dissociation as we would from a strong acid. So here's a weak acid, ethanoic acid. You'll remember that from our organic unit. Ethanoic acid is again doing what all acids do, giving away an H+, but this time it's forming an equilibrium. It's not all going to become ions like our strong acids do. So if we started with 0.1 mole of ethanoic acid, we actually don't know the number of moles of products that we would form, because we don't know to what extent it's going to dissociate, unless we have some more information. You should remember from last year that equilibria always have a K value, and that K value tells us to what extent the reaction has gone. Are there more products? Are there more reactants? What's the ratio? So we can write a K expression for an acid, and we're going to call that Ka. The A stands for acid, and the K is that equilibrium dissociation constant. So, how do we write these K expressions? Well, we always have the concentration of products on the top and the concentration of reactants on the bottom. So let's have a look. There's our products, CH3COO- and H3O+. Those two go on the top. And what are our reactants? CH3COOH and H2O. Now I've crossed out the H2O, and the reason is that we don't include liquids or solids in an equilibrium constant expression. The reason is that the concentration of a liquid or a solid is so high in relation to any dissolved particles, molecules or ions, or gases, that we can assume them to be constant. For example, water has a concentration of 55.6 moles per litre approximately. Now when we're dealing with 0.1 here, for example, that number is so large it's hardly going to change at all, so we can assume it to be constant, and therefore we'll leave it out of our K expressions. If we know the Ka values for weak acids, we can actually compare their strengths. Not all weak acids behave in the same way. They're all going to dissociate to different extents. Some might dissociate a tiny bit, some might dissociate a lot. So let's have a look at this table and see if we can compare them. So what we have here are 4 different weak acids, HCN, HOCl, CH3COOH and HF, and we have their corresponding Ka values in this column. What we can see is that as we go down the table, the Ka values get larger. Just take a moment to think about that. Yes, the Ka values do get larger because we're getting less zeros before these numbers if we were to write it in decimal form. You can see that comparing these numbers is quite tricky. It's not overly straightforward. And so what we can do to make things a little bit more straightforward for us is turn them into a pKa. Just as we turn H3O plus concentration into pH to make it more straightforward to compare, we can do the same thing for Kas and turn them into pKas. We use this equation here. pKa equals the negative log of the Ka. So that looks very similar to our pH equation. If I negative log all of these separate Ka values, I get these pKa values, which make them a little bit more straightforward to compare. So what can this table tell us? Well, it tells us that as we go down the table, the Ka values are getting larger, which means, in terms of an equilibrium, if I was to look back at my weak acid equation, as the Ka gets larger, it means I'm getting more and more products being formed, less and less reactants. So the larger the Ka value, the more products I'm getting, therefore the stronger the weak acid is. So as at the bottom of my table, with a larger Ka value, HF is a stronger weak acid than HCN, which is a smaller Ka value. Let's now use the pKa values. HF is going to be a stronger weak acid. We know that from our Ka being a larger value. And it has a smaller pKa value. So the lower the pKa value, the stronger the weak acid is. Therefore, HF is stronger than HCN because its pKa is 3.17 as opposed to 9.22. So pKa's are just a way of simplifying Ka information and helping us to compare acids. So on this table, we are getting stronger acids as we go down the table. They're all weak acids, there's no strong acids there, but we can compare how strong each weak acid is, i.e. to what extent does each acid dissociate. Let's do some quick calculations to make sure we're comfortable with this idea of Ka and pKa and how to convert between the two. So our first exercise is calculate the pKa of HNO2 given that its Ka value is 7.24 times 10 to the power of negative 4. Now might be a good time to pause this video and have a go at this calculation for yourself. I'll carry on. pKa equals, what was the equation again? Negative log Ka. First line, write your equation. Second line of working, now substitute in the values. So we're going to have the negative log, what was our Ka? 7.24 times 10 to the power of negative 4. Last line of working, plug it into your calculator and get the answer. Mine comes out as 3.14. There are no units for pKa, just as there are no units for Ka. Okay, second calculation. Calculate the Ka of ethanoic acid given the pKa equals 4.76. So we're going to need a second equation for this to get from pKa back to Ka. We use a very similar equation to the one we used to get from pH back to H3O+. Ka equals 10 to the negative pKa. So that 10 to the power of is effectively undoing the log base 10 that we did going the other way. So let's substitute in our values, equals 10 to the power of negative, my pKa is 4.76, and again plug that into your calculator, and what should come out is 1.74 times 10 to the power of negative 5. Again, no units for Ka. Okay, so we're now going to walk through the pH calculation for a weak acid, which does involve a significant number more steps than a strong acid does. So here's a question that we might work to. Calculate the pH of a 0.1 mole per litre ethanoic acid solution, and we're given the Ka for ethanoic acid. We can see the Ka is a very small number, which means again that our weak acid is hardly dissociating at all, which we do need to keep in mind as we go through this calculation. So there's going to be a very low H3O plus concentration relative to our starting concentration. So I've written it down as a number of steps. Step number 1 is to write a balanced chemical equation for the substance in water. Again, we've got ethanoic acid, so it's going to act as an acid and it's going to donate an H plus to the water, resulting in the ethanoate ion being produced and the hydronium ion being produced. What we've been told in the question is that we start with a 0.1 mole per litre ethanoic acid solution. Again, we have the issue, we don't know how much of this is going to react and turn into our products because we've got an equilibrium. We cannot assume that all of our acid dissociates, making all H3O plus like the strong acids do. So, we can apply some logic. We know some of it is going to dissociate, so let's call that some of it X. For every molecule that dissociates, one of these will be produced and one of these will be produced. So for every X number of molecules that react, we're going to get X number of ions produced. So this might be one molecule donating its H plus to a water. That would produce one of those and one of those. So that's just some applied logic there. We also need to keep in mind that a little bit of H3O plus is being produced by the dissociation of water itself. So there is going to be a little bit more H3O plus than CH3COO minus. We need to keep that in mind for our calculation too. To make our calculation a little bit more straightforward, we're going to make two assumptions, both valid. The first assumption is that we're going to assume that because so little ethanoic acid dissociates, none of it does. We are going to delete and ignore that X there. We'll call that assumption A, and I've written that below. Because so little ethanoic acid dissociates, proven by this very small Ka value, we will assume that none does. So we're going to assume that the ethanoic acid concentration is still 0.1 mole per litre. The second assumption we're going to make is that because so little H3O plus is added by the dissociation of water, we're also going to assume that none of that does. We'll call that assumption B, and I've written that below as well. The H3O plus ions from the dissociation of water, which is represented by the Kw, are so few that we can ignore them. And we'll do that throughout our calculation. So step 1, again, write the balanced equation. And it's good to do some thinking like this below the equation about what's actually going on in the reaction. Heading over to step 2 is to write your K expression. So as we can see from our equation, K expressions are always products, these two, over reactants, these two. And we're going to exclude the water because again it's a liquid, its concentration is so high we can assume it to be constant. So there's our K expression written. Step 3 is now to substitute in some values. We have the Ka from the question right at the start. We were given the Ka of the ethanoic acid, so I've input that there. We've also got the concentration of the ethanoic acid. We're going to assume it's 0.1, and we have the concentration of the two products. We're going to call each of them X. The aim of the game is to find the concentration of H3O+, because that's going to allow us to find the pH. So that's what we're working towards. So if I input both of those numbers, or all three of those numbers, X, X, and 0.1, my two products, each of them is X, my reactant, assumed to be 0.1. Step 4 is then to rearrange and solve. So here's a rearrangement. X times X, I'm calling X squared. It's still over 0.1, and I've just swapped the sides to make my unknown variable on the left-hand side. Working my way down with the rearrangement, I can multiply 0.1 across to the other side. So multiplying both sides by 0.1 brings it over to here. And then I can get rid of the squared by square rooting both sides. And that gives me X equals the square root of those two. Then I have to keep in mind that X is either the ethanoate ion or the H3O+ ion. I'm trying to find H3O+, so I'm at this point going to relabel it H3O+, like so. And that's what my calculator spits out when I square root 1.74 times 10 to the minus 5 multiplied by 0.1. It gives me 1.32 times 10 to the minus 3 mole per litre. Carrying on to my last step, step 5 now, I have the H3O+ concentration. Let's find the pH. So, there's my age-old equation. pH equals the negative log of H3O+. Plug in my just calculated H3O+ concentration of 1.32 times 10 to the minus 3 moles per litre. And that gives me a pH of 2.88, rounded at the third significant figure. So that's how to calculate the pH of a weak acid. And again, you can replay that section of the video if that would help your learning. A challenge for you now. Your turn. Calculate the pH of a 0.2 mole per litre solution of HOCl. Just note HOCl is a weak acid. It's not HCl, which is the strong acid. We also know it's a weak acid because we've been given a Ka value for our weak acid, 2.88 times 10 to the minus 8. Go ahead and work that out now. I'll reveal the answer in 5 seconds, so pause now. The answer to this question is 4.1. I hope you found this helpful. All the best, and I'll see you again in another video. Cheers.